Now I want to talk about types of convergences. This is another basic stuff you need to know, understand the language behind Carver and Thomas. They don't describe these things. They don't explain these things in details. So I have to supply these materials in order to help you understand the language used in the textbook. So types of convergences the textbook talks about is three things. First, convergence in distribution, which is this one. The first thing is this one, convergence in distribution, convergence in probability, convergence almost sure sense, or almost everywhere sense, or with probability 1. So these are the languages. And I will talk a little bit about L to norm convergence. Okay. So first one is the easiest one. We say that x1 is sequence of random variables parameterized by n converges to x in distribution if the distribution converges. So what do you mean by distribution converges? We call Fn of x defined to be probability of xn less than or equal to small x converges to f of x, which is probability of x smaller than or equal to small x as n goes to infinity. So what is the type of distribution that you can have an example? The easiest example could be, let's say, let me give you you can define xn to be, let's say, -1 over power of x and x, where x is a binary, +1 or -1 with a probability of f and f. So in terms of distribution, this distribution x of n is always equal to the distribution of x. So as n goes to infinity, or whatever the n is, the distribution stays the same. So we can say that xn converges to x in distribution. But we note that xn itself never converges to xn, to x. So xn never converges to x. xn is never equal to x, while the distributions are the same. So that's the weakest form of convergence. Another example of convergence in distribution is CLT, central limit theorem. If we let x1, x2, IID, fair binary random variables, so -n + 1, And we let Sn to be defined to be this with the xi up here, right here. It appears in the next line, but it's just the summation of all xi and divided by square root of n, the number of summations. Then the cumulative distribution of Sn converges to normal distribution. We call this central limit theorem. You can use the MATLAB M file to show this convergence. Hold on a sec, I will show you the M file. Convergence in distribution example. This one is interesting. I may use this example for the class materials. So let me show you. So convergence in distribution, you can use MATLAB file that I'll show you in the end of this note. We let x1, x2, and so on to be IID, fair binary random variables. And we let Sn to be the summation of all xi, normalized with 1 over square root of n. Then Sn converges, oops, what happened? Sn converges to Gaussian random variable, Gaussian normal, with mean 0 and variance of 1. Okay, such that the cumulative distribution converges to the normal distribution. And then we can evaluate the expression for n is equal to 6 and see what happens. Oops, so there is a typo here. So let me use the square root. Okay, so I corrected it. So S6 is defined to be this, following the general distribution, general description given right here. So what is the dimension of random variable S6? Again, there is a typo. Let me correct it. Instead of 5, it is supposed to be 6. And the answer is normalized by square root of 6. It should be minus 6 to 6. So for example, if all xi's, all 6 xi's are plus 1, it is 6. Okay, and all 6 xi's are minus 1, should be minus 6. And 5 plus 1 and 1 minus 1, which should be 4, 2, 0, and so on and so on. And let the random variable to be fair. So probability of minus 1 and plus 1 are equal to each other, which is 1/2. So it is plus 1 with a probability of half, minus 1 with a probability of half. Now let us see the distribution of S6. So S6, all taking, when S6 is equal to this value, that means 6 at the top. That means all 6 xi's are plus 1. That occurs with probability of data. So this is supposed to be, I think, has to be changed to be plus 1. Sorry about that. Okay, but it doesn't change the result anyhow. So all 6 plus 1. So that is data to the 6th power. And then when S6 is equal to minus 4 over square root of 6, that is equal to 6 choose one position. And in one position you have minus 1, and all 5 rest of the 5 positions plus 1s. So that's this probability. And then 6 choose 2 plus 1s, and then rest of them minus 1s. And then so on and so on. Okay, so that's the distribution of this random variable. And then you can obtain the cumulative distribution by taking the summation starting from negative infinity to positive infinity. And then we can compare that distribution, cumulative distribution, with the cumulative distribution function of the normal random variable, which is given by this expression. And then we can compare that with, compare the two distributions. So for example, this is the normal distribution, and this is distribution of S6. And use this random variable, use this M file to plot the picture for different n. Here I use capital N. So n is equal to 200 means that you have 200 point masses in the probability mass function, or 200 steps in the cumulative distribution function. So this is the case when n is equal to 6. If you have 200, then you use that M file to see that it is as close as to the normal distribution. So you can use this M file to draw the CDF comparison and verify convergence in distribution. This talks about convergence in distribution. Convergence in distribution does not mean that the random variable itself converges. It only shows convergence of distribution. Okay, so that's convergence in distribution. Now I want to talk about convergence in probability. We say that random variables xn converges to x in probability as n goes to infinity if for each epsilon greater than 0, the probability of set omega, where xn of omega minus x omega absolute value greater than epsilon converges to 0 as n goes to infinity. So this is the probability of deviation set. So collection of all omega that xn deviates from x by epsilon much. The probability of such a set goes to 0. That's what convergence in probability means. I will give you some example later on. Convergence, almost sure sense, or almost everywhere sense, or with a probability of 1, is xn converges to x, almost sure sense, as n goes to infinity, if one of the following holds. So the first item, let me see. So this is the first item. Second item is this, and then third item will appear in the next page. So first item says this: if probability of set of omega limit xn of omega is equal to x omega. So limitation of this random variable is equal to x omega, and probability of collection of such omega is equal to 1. Okay, so make sure that this is satisfied for each omega in the set. And then probability of such a set is equal to 1. So that's what almost everywhere sense, almost the sure sense convergence. That can be written in other form, as the second line says. For each epsilon greater than 0, probability of set of omega, where xn omega minus x omega absolute value greater than epsilon, infinitely often. So this is infinitely often. Okay. So probability of such a set is 0. So probability of deviation set is equal to 0 as n goes to infinity. And the third item, this is first, second, and third, for each epsilon greater than 0, for any epsilon greater than 0, limit k goes to infinite, probability of union of n greater than or equal to k, and union here says that one is greater than epsilon. Okay, so that is the set of omega. So set of omega, and this probability, so deviation, should go to 0. Okay, so for each epsilon should go to 0. as n goes to infinity. So these are the three items. The probability of deviation set should go to 0. Okay. Since this should go to 0, then the deviation probability of deviation set goes to 0. Oh, sorry. And then probability that xn is equal to x goes to 1. Okay. So these are the three items, and this is the definition for L2 norm sense convergence. Xn converges to x in L2 norm sense if the L2 norm converges to 0. So if the L2 norm of the deviation converges to 0 as n goes to infinity. Okay.